Chemical properties and compounds of group 16 elements. Chemical properties and compounds of group 16 elements. Okay? Hydrides. All the elements of group 16 form hydrides of the type H2X. Okay? All the elements of group 16 form hydrides of the types of H2X. Okay? Example: H2O, H2S, H2SE, H2TE, and H2PO. Okay? Oxygen and sulfur also form the hydrides like H2O2. Oxygen and sulfur forms hydrides H2O2 and H2S2, H2S2, and H2O2 is stable and oxidizing agent. H2O2 H2O2 is stable and oxidizing agent. Oxidizing agent. Whereas H2S2 is unstable. Okay? The structure of both the compounds are approximately same, and bond angle in angle HOO and angle HSS are 97 degree and 104 degree respectively. Okay? Next heading: preparation. Next heading: preparation. Okay? Water is formed by combination of hydrogen and oxygen. Okay? Water is formed by combination of hydrogen and oxygen present in atmosphere. The hydrides of sulfur, selenium, tellurium are obtained by the action of acids and metal sulfides, selenides, and tellurides. Okay? Then FeS plus H2SO4. H2SO4, that is FeSO4 plus H2S. Okay? And K2SE plus H2SO4, that make K2SO4 and plus H2Se. Okay? The hydrides are bad smelling poisonous gases. The hydrides are bad smelling poisonous gases at ordinary temperature. Water is a exception, which is a colorless and odorless liquid. They can be easily liquefied and solidified. Some important properties of dihydride are given as follows. First point is volatility. First point is volatility. The volatility increases from water to H2O to H2S, and then after decreases. This trend is explained by their boiling points given below. Hydride and boiling point K. Okay? Hydride H2O, H2S, H2Se, H2Se, and H2Te. Okay? 373, 213 Kelvin, and 232 and 269 Kelvin. Okay? Boiling point. Okay? Water has abnormally low volatility and possesses high boiling point. Water has abnormally water has abnormally low volatility, low low volatility and possesses high boiling point and possesses high boiling point. This is due to the association of molecules. This is due to the association. This is due to the association of molecules. This is due to the association of molecules through hydrogen bonding. Through hydrogen bonding in solid and liquid states. In solid and liquid state solid and liquid state. Okay, water has abnormally low volatility and possesses high boiling point. This is due to the association of molecules through the hydrogen bonding in solid and liquid state. Next point, hydrogen bonding. What is hydrogen bonding? We will be study about hydrogen bonding, how to work hydrogen bonding, and what is the angle between hydrogen bonding. Okay. Next is the hydrogen bonding in H2X. Hydrogen bonding in H2X. Okay. 1 minute. Hydrogen bonding. Next, second point. Hydrogen bonding. Hydrogen bonding. Okay. In H2X. H2O shows hydrogen bonding due to large electronegativity difference between oxygen and hydrogen and small size of oxygen. Okay, this is a hydrogen plus sigma bond oxygen, that is a hydrogen plus sigma bond minus sigma bond. This is hydrogen plus sigma bond. This is oxygen plus sigma bond hydrogen minus sigma bond. This is hydrogen and plus sigma bond and single bond oxygen plus sigma bond hydrogen. This is minus sigma bond and this is hydrogen and plus sigma bond and single bond oxygen, single bond hydrogen plus sigma bond minus sigma bond and triple bond H2OX. Okay. Due to hydrogen bonding has high molecular weight and is a liquid. Due to hydrogen bonding H2OX has high molecular weight and is liquid. High molecular weight and is liquid. Okay. The electronegativity difference between sulfur and hydrogen is low and the size of the sulfur is large. Hence, there is no hydrogen bonding in H2S, hydrogen sulfide, and its molecular weight is low compared to water. Thus, H2S exists in gaseous form. H2S exists in gaseous form. Similarly, there is no hydrogen bonding and H2SC. There is no hydrogen bonding in H2SC and H2PE. Okay. Next point, thermal stability. Third point, thermal stability. Thermal stability, okay? And non-metallic character decreases, thermal stability also decreases. The thermal stability of the hydrides of group 16 decreases with rise in molecular weight. The thermal stability of the hydrides of group 16 decreases with rise in molecular weight. Decreases with increase or rise in molecular weight. Okay? Molecular weight. Water dissociates at high temperature 2000 degrees Celsius. Okay? Water dissociates at high temperature approximately 2000 degrees Celsius, while H2S dissociates at 400 to 600 degrees Celsius and H2SI dissociate at 100 to 150 degrees Celsius, while H2T decompose even at ordinary temperature. Ordinary temperature, okay? Ordinary temperature. Covalent character. Next point, covalent character. Fourth point, covalent character. Covalent character gradually increases from H2O to H2T. This is due to decrease in electronegativity value from oxygen to tellurium and increase in ionic radii from oxygen double negative to tellurium double negative. Okay? Covalent character. Okay? Covalent character gradually increases from covalent character gradually increases from H2O to H2T. Okay? This is due to decrease in electronegativity value from oxygen to tellurium and increase in ionic radii from O to negative. Okay? And next point, reducing property. Reducing properties. Okay? Reducing properties. Okay? H2O is less than H2S is less than H2SE is less than H2T. Okay? As metallic character increases from oxygen to tellurium. As metallic character increases from oxygen to tellurium, reducing power. H2X increases from increases from H2O to H2T. Okay, acidic strength. Okay, next point, acidic strength. Okay, 1 minute. Acidic strength. Next point, acidic strength. Acidic strength. Stability of the hydrides decreases with increase in atomic number. Acidic character increases from acidic character increases from acidic character increases from H2O to H2Te. Okay, H2O is the less than H2S is the less than H2Si is the less than H2Te. Okay, as the radius of X double negative increases, the attraction between hydrogen and oxygen decreases. The attraction between hydrogen plus and X double negative decreases. Hence dissociation of H2X H positive plus HX negative. Okay, increases, and thus acidic strength also increases. The radius increases in order to oxygen, sulfur, selenium, tellurium, and so acidic strength has been order given as above. Okay, next 7th point, acidic strength of hydrogen and H2 peroxide. Acidic strength of H2O, but that means water, and hydrogen peroxide H2O2. Okay, the oxidation state of oxygen in H2 is -2. The oxidation state of oxygen in water is -2, and in hydrogen peroxide is -1. The -1. Okay, the hydrogen ion is more attracted with the hydrogen anion is more attracted with oxygen double cation. Okay, hence dissociation of hydrogen, dissociation of water H2O is H positive ion plus OH negative ion is less than in H2O2, that make H positive ions plus HO2 negative ions. Okay, thus the acidic strength order is as thus acidic strength order is as H2O is less than H2O2. Okay. Next, bond angle. Bond angle. Next, 8 point. Bond angle. Bond angle. Bond angle. Bond angles. Okay. Bond angle. Next point. Bond angles. The bond angles. Bond angle. HXH. The bond angles HXH in H2O. In H2O. H2O. H2S. H2S and H2TE are 104.5 degree, 92.5 degree and 90.0 degree and 89.0 degree, okay, respectively. In water molecules, central atom oxygen is in sp3 hybridization having two lone pairs of electrons. Due to presence of lone pair according to BSEPR theory, bond angle decreases. The HOH, hydrogen oxygen hydrogen bond angle is of the order of 104.5 degree in water with slight distortion. The shape of H2O molecule of V type in H2SE and H2TE bond angles are nearly 90 degree, which suggests that almost pure p orbitals of selenium and tellurium are participating in bonding to hydrogen atom. Okay. You can listen carefully. Okay. The bond angle hydrogen halides and hydrogen in H2O, H2S and H2SE and H2TE are 104.5 degree, 92.5 degree, 90 degree and 89 degree respectively. In water molecules, central atom oxygen is in sp3 hybridization having two lone pairs of electrons. Due to presence of lone pairs according to BSEPR theory, bond angle decreases. The hydrogen oxygen hydrogen bond angle is of the order of 104.5 degree in water with a slight distortion. The shape of water molecule is of a V type. In H2SE and H2TE, bond angles are nearly 90 degree, which suggests that almost pure p orbitals of selenium and tellurium are participating in bonding to hydrogen atoms. Okay. And next point, highlights. And property, melting point of water is 0 degree and H2S is minus 85.5 degree and H2SE is minus 65.7 degree and H2TE minus 15.1, and boiling point of water 100 degrees Celsius and H2S is minus 60.75 and H2SE is 41.5 and you can show 1 minute. Melting point, boiling point, dissociation temperature, bond angles, and dissociation constant, Ka at 25 degrees Celsius, and odor. Okay. The water and H2S, H2SE, H2T. The boiling point of melting point of water 0, and H2S minus 30.5 and 65.7 and minus 15.1. Okay, minus 15.1. And boiling point 100 degrees Celsius, and H2S is minus 60.75 and minus 41.5 minus 1.8. And dissociation temperature of water is 2000, and H2SI is 400 to 600 and 150 and 0. And bond angles 104.5, 92.5, 90 degree and 89 degree. And dissociation constant K at 25 degree is 1.0 into 10 to the power minus 14 and 1.0 into 10 to the power minus 7 and 1.7 into 10 to the power minus 4 and 2.3 into 10 to the power minus 3. Odorless, water is odorless, and H2S is like rotten eggs, like rotten eggs, and H2SI is pungent smell, and H2T is pungent smell. Okay. Next point, highlights. Okay. Next point, highlights. 1 minute. Highlights. Okay. The element of group 16 form many highlights of the type MX2, M2X2, MX4, and MX6. Okay, the main highlights are given. You can show. And oxygen, sulfur, selenium, tellurium, and polonium, fluoride, bromide, and iodide. Okay. Then fluoride, F2O2 and F2O. Chloride, Cl2O, ClO2 and Cl2O6 and Cl2O7. Okay. And bromide, Br2O, BrO2 and BrO3. Okay. And iodide, I2O, I2O4 and I2O5. The oxygen. Okay. And sulfur, H2F2, SF4, SF6, H2F10, and chloride. So chloride of sulfur is H2Cl2, SCl2, SCl4, and bromide H2Br2. Okay. And selenium. Next element is selenium. Se2F2, SeF4, SeF6, and Se2Cl2, SiCl4 and Si2Br2, SiBr4, okay, and tellurium, TeF4, Te2F10, TeF6, and TeCl2, TeCl4, and TeBr2, TeBr4, and TeI4, and polonium, PoCl2, PoCl4, PoBr2, PoBr4, and PoI4. Okay, oxygen does not easily combine with halogen. Oxygen does not easily combine with halogens, but fluorine oxide F2O and oxides of fluorine and bromine are formed with difficulty. Sulfur, selenium, tellurium combine directly with halogens and form halides. Okay, and form halides. Example: SF6, SiF4, TeF4, SiCl2, and TeCl2, etc. Okay. Okay. Next is electronegativity of fluorine is more than oxygen. Electronegativity of fluorine is more than oxygen. Hence its compounds are called fluorides of oxygen. Since electronegativity of fluorine, bromine, iodine is less than oxygen, thus compounds of these halogens with oxygens are called oxides. The OF2 is named as oxygen difluoride. The OF2 is named as oxygen difluoride, and Cl2O7 is called chlorine hydroxide, and Cl2O7 is called chlorine heptoxide, chlorine heptoxide. Okay. Next heading hexahalides. Okay. Hexahalides. As metallic character increases, ease of formation of SF6 increases, then SF6 is the less than SeF6 is the less than TeF6. Okay. Hexafluorides are the only stable compounds amongst halides. Amongst hexahalides, sulfur, selenium, and tellurium combined directly with the fluorine to form SF6, and TeF6 hexafluorides respectively. Okay. In hexafluoride, the nature of hybridization is sp3d2. Thus, the structure of hexafluorides are octahedral, and the structure is octahedral. Okay, octahedral. And in SF6 molecule, and thus the structure of hexafluoride is octahedral in SF6, in SF6 molecule. In SF6 molecule, SF6 molecules, sulfur has 6 sigma bond. Sulfur has 6 sigma bond. Sulfur has 6 sigma bond and need 6 equivalent orbital obtained by sp3d2 hybridization. Hence the structure is octahedral and shape is also octahedral. The structure of the SF6 you can show. This is sulfur and this is fluorine, this is fluorine, this is fluorine, this is fluorine. Okay, fluorine, fluorine and fluorine, and this is fluorine and fluorine, fluorine. Okay, octahedral structure of SF6, structure of SF6. Okay, structure of this is the structure of SF6. Okay, SF6 is extremely stable, extremely stable. SF6 is extremely stable, extremely stable. Okay, SF6 is extremely stable. Okay, SF6 is extremely stable and behave chemically as inert. SEF6 is slightly more reactive than TEF6 is still more reactive. Okay, all hexafluorides are colorless gases. All hexafluorides, all hexafluoride, okay, all hexafluoride is gas, colorless gas, is a colorless gas. Okay, colorless gases, all hexafluoride is colorless gases. Okay, all hexafluoride is colorless gases. Other halogens do not form the hexafluorides. Other halogens do not form the hexafluorides. Okay, as the size of the halogen atom increases, the coordination number of the element decreases. That is why hexafluorides, hexabromides and hexaaldehydes do not form. Okay, next heading, next is pentahalide. Next is pentahalide. Next is pentahalide. Okay, pentahalide. Only one pentahalide of sulfur is known as exists in the dimeric form like H2F10. H2F10. Only one pentahalide of sulfur is known as it exists in dimeric form like H2F10. Third point, tetrahalide. Okay, tetrahalide. All halogens forms tetrahalides. Okay, all halogens forms tetrahalides. All halogens form tetrahalides. All halogen forms tetrahalides. Okay. Tetrafluorides cannot be obtained by direct combination of the elements with fluorine. Tetrafluoride can be obtained by indirect method. As an example, we talk about the example of tetrahalides. All halogens form tetrahalides. Tetrafluorides cannot be obtained by direct combination of the elements with the fluorine, and tetrafluorides can be obtained by indirect method. As an example, 3HCl2 plus 4NaF at 75 degrees Celsius, H2Cl2 plus SF4 plus 4NaCl, SeCl4 plus 4AgF silver fluorine that make SeF4 plus 4 silver chloride AgCl and Te plus 2F at 0 degrees Celsius TeF4. Okay? SF4 is a gas. SF4 is a gas. SF4 is gas. Okay? SF4 is gas. SiF4 is liquid. Is a liquid. Okay? While SeCl4 is solid. SeCl4 is solid. Okay? SeCl4 is solid, and TeCl4 are solid. Okay? SbR4 is also unstable and get easily hydrolyzed. Okay? SiBr4 is very stable. Only TeI4 is stable compound amongst the tetraiodides. Okay? The stability of tetrahalides MX4. The stability of tetrahalide MX4. The stability of tetrahalide. Okay, 1 minute. The stability of tetrahalides MX4 increases from sulfur to tellurium. They are called hydrolyzed by water, giving the oxy acids XO and OH2. Okay, then TeCl4 plus 3H2, that make H2TeO3 plus 4HCl. Okay. In tetrahalides there is sp3. In tetrahalides there is sp3d hybridization. Okay. Central atom M has 4 sigma bonds and 1 lone pair needs 5 orbitals obtained from sp3d hybridization. Thus tetrahalides have a trigonal bipyramidal structure with a lone pair of electrons at equatorial position. The structure of tetrahalide you can show molecules: chlorine, and okay, this is chlorine, this is chlorine. Okay, this is the structure of tetrachloride. Okay. Next heading, dihalides. Okay. Next heading, dihalides. 1 minute. Dihalides. Okay. All the elements of group 16 form stable dichlorides and dibromides, except selenium diiodides do not exist. Okay. SCl2 is best known dihalide. It is formed by saturating H2Cl2 with chlorine at normal temperature. H2Cl2 plus Cl2 at NTP normal temperature and pressure 2SCl2. And TeBr2 is formed by direct combination of TeBr2 T plus Br2 that make TeBr2. In dihalides there is sp3 hybridization. Hence the structure of dihalides should be tetrahedral structure. Tetrahedral structure, but due to presence of 2 lone pairs, the normal tetrahedral bond angle 109 degree 28 minutes. According to VSIPR theory, the repulsion between 2 lone pairs is more than the repulsion between 2 bond pairs, are between a lone pair and bond pair. That is why the bond angle in SCl2 is a 103 degree, and OF2 is a 101.5 degree, and TeBr2 is a 98 degree. The structure of SCl2, you can show the structure of SCl2: sulfur, that is chlorine, lone pairs, that is chlorine, okay, chlorine, okay, okay, 103 degree, 103 degree, okay. Structure of sulfur dichloride. This is the structure of sulfur dichloride. This is the structure of sulfur dichloride, okay. Next heading is monohalides. Okay. Next heading, monohalides, okay. Next heading, monohalides. Monohalides exist in dimeric form like S2, F2, SI2, Br2, O2, F2, SI2, Cl2, H2, Cl2, okay. Monohalides are hydrolyzed slowly and undergo disproportionation. Example 2s2Cl2, 2s2Cl2 plus 2H2O, that make 3s plus SO2 plus 4HCl, okay. And 2SiCl2 is SiCl4 plus Si, okay, plus Si, okay. Structure of monohalides is just like the structure of H2O2. Monohalides possesses sp3, sp3 hybridization, and bond angle is 104 degrees Celsius, started due to presence of two lone pairs of electrons. On the basis of electron diffraction study, the structure of monohalides S2F2, S2Cl2, etc. is monoplanar like H2O2 and FSS and ClSS. Bond angle 104 degree, okay. Then this is sulfur 1, 2, 3, 4, and this is chlorine, and this is chlorine, and 2.02 angstrom, and sulfur, that is 104 degree, 1.99 angstrom, okay. This is the structure of sulfur monochloride, H2Cl. So next heading, compounds with carbon. Compounds with carbon, okay. Compounds with carbon, okay. The element of group 16 form compounds with carbon like CO2, CO2, CH2, CSI2, okay, CSI2, and CTE, okay. Only oxygen forms monoxide. Only oxygen forms Oxygen forms only oxygen forms monoxides. Monoxides. Only oxygen forms monoxides. Okay. Oxides. Oxides. Fourth point. Oxides. Oxides. Okay. The element of group 16 form several types of oxide which are you can show monoxide, dioxides, and trioxides and heptoxides. Heptoxides, oxides, okay? That is sulfur, sulfur, selenium, and tellurium, and polonium, polonium. Monoxide of sulfur is SO, and dioxide of sulfur is SO2, and trioxide of sulfur is SO3, and heptoxide of sulfur is H2O7. Selenium, not monoxide, dioxide SiO2, trioxide SiO3, and not heptoxide, okay? And tellurium is TeO2 dioxide, TeO3 trioxide, and polonium is polonium oxide, polonium monoxide, polonium dioxide, and not trioxide, and not heptoxide. Oxides of sulfur are more stable than other oxides of group 16 elements. Only sulfur forms of suboxide, sesquioxides, heptoxide, and sulfur tetraoxide. The various oxides of sulfur, you can show the various oxides of sulfur, okay? Okay, then H2O, that is sulfur suboxides. Sulfur suboxide, that is colorless gas. That is colorless gas, unstable. That is colorless gas, unstable. Next is SO, sulfur monoxide. Sulfur monoxide, that is colorless gas, very reactive. Colorless gas, very reactive, okay? Next, H2O3, that is sulfur sesquioxide. That is sulfur sesquioxide. That is bluish green. That is bluish green, crystalline, bluish green crystalline solid, decomposes slowly. Okay. Next is SO2, sulfur dioxide. Sulfur dioxide. Next is sulfur dioxide. This is a stable colorless gas. Stable colorless gas having stable colorless gas having odor of burning sulfur. Odor of burning sulfur. Next is SO3, sulfur trioxide. Sulfur trioxide. Next is sulfur trioxide. This is a volatile liquid, exists in three forms. This is volatile This is volatile liquid, and exists in three forms. Exist in three forms. Okay, and next is H2 H2O7, that is sulfur heptoxide, that is sulfur heptoxide, that is viscous liquid. Okay. SO2 sulfur dioxide, that is colorless gas, unstable. H2O sulfur suboxide, colorless gas, unstable. Okay. And SO sulfur monoxide, that is colorless gas, very reactive. And next is H2O3 sulfur cisco oxide, that is bluish green crystalline solid and decomposes slowly. And the next is sulfur dioxide, SO2 stable colorless gas having odor of burning sulfur. And SO3 sulfur trioxide volatile liquid, exists in three forms. And next is H2O7 sulfur heptoxide, that is viscous liquid. Okay, all the elements of the group 16 form MO2 type oxides except selenium. Okay, except selenium. Sulfur monoxide is formed by passing electric discharge through SO2 plus S, that is electric discharge and 2SO sulfur monoxide. Okay. Other monoxides are found by heating the corresponding trioxides. Okay, and next we will be study about the ozone. Ozone is considered as an oxide of the oxygen. Okay, and ozone gas is very useful in our life, that save us the electro radiation wave from of the Surya. Okay, sun. Okay, and next we will be studying about sun, ozone gases. Okay, thanks. Ozone. If ozone is considered as an oxide of oxygen, then carbon dioxide, then all the elements of group 16 form oxides of the type MO2. The oxides of sulfur, selenium, tellurium, sulfur dioxide, selenium dioxide, tellurium dioxide are acidic. The dioxide, sulfur dioxide, selenium dioxide, tellurium dioxide are the most stable oxides of the combustions of the group. If ozone is considered as an oxide of oxygen O2, then all the elements of group 16 form oxides of the type MO2. The oxides of sulfur, selenium, tellurium is that sulfur dioxide and selenium dioxide, tellurium dioxide are acidic. Okay, acidic. The dioxide, sulfur dioxide, selenium dioxide, tellurium dioxide are the most stable oxides of the combustions of the group. These are found from the combustions of the elements in air or oxygen. Sulfur dioxide is an easily liquefiable gas with choking smell, while as selenium dioxide and tellurium dioxide are colorless crystalline solid. Selenium dioxide and tellurium dioxide are colorless crystalline solid. Okay. Sulfur dioxide is an angular molecule, bond angle 120 degree, and sulfur dioxide is an angular molecule. Bond angle is 120 degree. Okay, and selenium dioxide consists of long zigzag macromolecule chains. Macromolecules chains. Okay, tellurium dioxide exists in two forms, one having a rutile TiO2 and other are brochite type. Okay, brochite type. Okay, that is a TiO2. Okay, lattice. Okay, their solubility in water, acidity and stability decreases from sulfur dioxide to tellurium dioxide. Okay, their solubility in water, and acidity and stability decreases from sulfur dioxide to tellurium dioxide. Okay, sulfur dioxide dissolves in water forming H2SO3, which is known as solution only. Tellurium dioxide is insoluble in water. Okay, and SO2 soluble in water, and that form H2SO3, which is known in solution only, and tellurium dioxide is insoluble in water. Okay, then sulfur dioxide plus water that make H2SO3, that is sulfuric acid. H2SO3 sulfuric acid, and selenium dioxide plus H2O that make H2SiO3 that make selenous acid. Okay, that makes selenous acid. With hot pumped nitric acid, selenium and tellurium are oxidized to H2SiO3 and H2TiO3, which on dehydration gives SiO2 and TiO2. Okay, respectively. Sulfur dioxide is a gas at room temperature. Okay, with hot nitric acid, selenium and tellurium are oxidized to H2SiO3 and H2TiO3, which on dehydration gives SiO2 and TiO2 respectively. Okay, sulfur dioxide is a gas at room temperature. Selenium dioxide is a volatile solid, while tellurium dioxide and polonium dioxide are non-volatile crystalline solid, reducing property oxides. Okay, and SO2 sulfur dioxide is gas at room temperature. And SiO2 selenium dioxide is a volatile solid, and TeO2 and PbO2 and PCOO2. Polonium dioxide and tellurium dioxide are non-volatile crystalline solid, non-volatile crystalline non-volatile crystalline solids, okay. Reducing property of oxide decreases from sulfur to tellurium, okay. reducing property reducing property reducing property of oxides reducing property of oxides decreases from sulfur to tellurium. Sulfur dioxide acts as both as oxidizing and a reducing agent, while tellurium dioxide is only an oxidizing agent. Sulfur dioxide both work as oxidizing and reducing. Oxidizing and reducing. Otherwise, tellurium dioxide is only work as oxidizing agent. Okay. In sulfur dioxide in +4 oxidation state, it can go to +6 oxidation state when it behaves as a reducing agent. Okay. 1 minute. Sulfur dioxide in +4 oxidation state. +4 oxidation state, it can go to +6 oxidation state when it behaves as a reducing agent. When it behaves as a reducing agent, okay. SO2 sulfur dioxide plus I2 iodine plus 2H2O, that make sulfur SO4 2 negative plus 2I negative plus 4H positive, okay. When sulfur in sulfur dioxide plus 4 oxidation state go to sulfur state, it behaves as an oxidation state, SO2 plus 2H2S, that makes 2H2O plus 3S, okay. Sulfur dioxide, the structure of sulfur dioxide may be represented by the following resonating, okay. This is sulfur 1 2 double bond, oxygen 1 2 3 4, and that oxygen 1 2 3 4 5 6, that is so the lone pair, and that is make sulfur 1 2 and oxygen 1 2 3 4 5 6, and double bond oxygen 1 2 3 4, okay. The bond angle OSO is 119.5 degree, indicates sp2 hybridization of sulfur, okay. Okay. And one sp2 orbital carries the lone pair of electrons, and another sp2 orbitals with a paired electrons make the coordinate bond with one oxygen atom. The electron in the third sp2 orbitals overlaps with an unpaired electron in the 3p orbitals of sulfur, then overlaps with a suitable orbital of the second oxygen to form the bond. Thus the double bond is formed, okay. Sulfur has a double sigma bond, and a lone pair, and needs 3 equivalent orbitals obtained by sp2 hybridization. The structure is triangular plane, shape is angular, and pi bond is formed by dp overlap, okay. This is the sulfur double bond oxygen, and one lone pair, that makes the structure is that, okay. And this is the sulfur double bond oxygen, and the angle between sulfur oxygen is 119.5, and this is lone pair, this is 1:43 p.m. Okay, and this is the structure of sulfur dioxide. Structure of sulfur dioxide. Okay, the sp2 hybridization and p-pi. The sp2 hybridization and p-pi bond, p-pi bond, and p-pi d-pi bond, d-pi bond in sulfur dioxide. In sulfur dioxide molecules represented by, you can show, okay, and you can show the structure of sulfur dioxide in next 1 minute. You get, and that is the oxygen atom in ground state. Oxygen atom in ground state is you can make, this is 1, 2, 3. Okay, 1. This is oxygen atom in ground state. Oxygen atom in ground state, and that is make single sp2 hybridization. This is sp2 hybridization. This is sp2 hybridization. sp2 hybridization. sp2 hybridization. This is sp2 hybridization, and that p-pi bond, p-pi bond, and that is p-pi bond, and 1, 2, 3. That is 1, 2. That is p-pi bond, p-pi bond, oxygen atom in ground state. Oxygen atom in ground state. Oxygen atom in ground state, and that is oxygen atom in ground state, and 1, 2, 3, 4, and 5. That is sulfur atom in excited state. Sulfur atom in excited state. Okay, so structure of sulfur dioxide molecule found by sp2 hybridization of sulfur atoms. Selenium dioxide is a white volatile solid. The structure of selenium dioxide is similar to that of sulfur dioxide in gaseous state, but in solid state it has infinite chains which are non-planar, and given, you can show oxygen single bond, selenium, and double bond oxygen, and that is 178 pm. That angle is 90 angles. Oxygens and selenium double bond oxygen, that is 173 pm, and that angle is 90. That angle is 90. Okay, that angle is 98 degree. That angle is 98 degree. That angle is 98 degree. Oxygen, and that make 125 degree, and selenium, and double bond oxygen, and so on. Okay, tellurium dioxide and polonium dioxide are non-volatile crystalline ionic solid. Sulfur trioxide, selenium trioxide, tellurium trioxide of group 16. sulfur trioxide is most important among them. Sulfur trioxide is obtained by the oxidation of a sulfur dioxide, oxidation of a sulfur dioxide, oxidation of sulfur dioxide. Okay. Oxidation of sulfur dioxide. The trioxide XO3 are the anhydrides of the acidic H2XO4, namely sulfuric H2SO4, selenic H2SiO4, and telluric H2TeO4. The anhydrides, sulfur trioxide and selenium trioxide, dissolve in water to give H2SO4 and H2SiO4. All trioxides are acidic in nature and form acidic dissolving in water. Okay. You can show SO3 plus H2O, that make H2SO4, and SiO3 plus H2O, that make H2SiO4, selenic acid, and TeO2 plus 3H2O, that make H6TeO6, that is telluric acid, okay. Oxy acids of tellurium in +6 oxidation state is +6 tellurium, TeO6, which is very weak acid, okay, very weak acid, okay. Which is very weak acid, okay. And sulfur trioxide SO3, the maximum covalency sulfur is 6 and show 12 extra electrons around sulfur, okay. SO3, sulfur, double bond oxygen, single bond oxygen, that make 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, and that is make sulfur, oxygen, double bond oxygen, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, and that make sulfur, double bond oxygen, 1, 2, 3, 4, and single bond oxygen, 1, 2, 3, 4, 5, 6, and single bond oxygen, 1, 2, 3, 4, 5, 6, and triple bond sulfur, oxygen, and 120 degree and oxygen, okay, and that make sulfur, double bond oxygen, and double bond oxygen, 1, 2, 3, 4, and 1, 2, 3, 4, and 1, 2, 3, 4, okay. And next here sulfur has 3 sigma bonds and 3 equivalent orbitals are obtained from sp2 hybridization. Its structure is planar triangular, the shape also planar triangular. Here sulfur has 3 sigma bonds and the 3 equivalent orbitals are obtained from sp2 hybridization. Its structure is planar triangular, the shape is also planar triangular, okay. 1 p orbital of sulfur forms a bond with p orbitals of oxygen. The extremely short bond length SO is 1.43 angstrom, okay. Points to additional bonding between filled p orbitals of oxygen and vacant d orbitals of sulfur. In gaseous state, sulfur trioxide has planar triangular structure, but in solid state it exists on cyclic trimer SO3 all thrice from form a linear chained structure. Solid selenium trioxide assists in a cyclic tetrameter sulfur selenium trioxide whole 4, but tellurium trioxide assists in network structure in solid state. Okay, you can show the structure of both is this is oxygen, single bond sulfur, double bond oxygen. Okay, 1 2 3 4 and 1 2 3 4 5 and 6, and that make oxygen 1 2 3 4, sulfur double bond oxygen 1 2 3 4 5 and 6. Structure of gaseous sulfur trioxide. Structure of gaseous sulfur trioxide. Gaseous sulfur trioxide, that is oxygen and sulfur and oxygen, and that angle is 119.5 degree, and okay, and next structure of solid sulfur trioxide, cyclic trimolecular. You can show how to the sulfur oxygen sulfur oxygen and oxygen okay, this is structure of solid SO3 cyclic trimolecular. Okay, next sulfur oxygen sulfur 1 oxygen 2 oxygen 3 and 4, and sulfur 1 2 3 and 4. Okay, and next is selenium 1 2 3 4. Okay, and selenium oxygen selenium oxygen. Okay, this is cyclic tetramolecular changed form. This is cyclic tetramolecular changed form of SeO3. Okay, next oxy acids. Next study oxy acids. Okay, oxy acids. Next oxy acids. Okay, sulfur selenium tellurium form similar types of oxy acids and salts which are given. You can show sulfur oxy acids formula. Oxy acids formula, oxyacids, formula, okay, and name of acid, name of acid, and salts, okay, sulfur, H2SO4, H2SO3, sulfurous. That the name of H2SO3 is sulfurous, and salt, sulfide. Next, H2SO4, that is sulfuric. The name is sulfuric, and the salt is sulfate, okay, and next is H2SeO3, selenium, okay, H2SeO3, selenious, that is selenious, okay, and selenite, salt is selenite. Next is H2SeO4, that is selenic. That name is selenic, and salt is selenate. Salt is selenate, okay, salt is selenate, okay, and next is tellurium. Next, tellurium, okay, H2TeO4, H2TeO3, H2TeO3, that is tellurous, that is tellurous, and salt is tellurite, okay, and next H2TeO4, the name is telluric, and that make tellurate, and the name tellurate, okay. Next study. Sulfur forms a large number of oxyacids. Out of these acids, some acids do not exist in a free state, but their anions and salts are known. The main oxyacids of sulfur are given in next table, okay. Name, formula, and remark. Name, formula, and remark, okay. Name, formula, and remark, okay. Name, formula, and remark, okay. Acids containing one sulfur atom. Acids containing one sulfur atom. One sulfur atoms. First point, sulfoxylic acid, okay. Sulfoxylic acid. That formula is H2SO2, okay. Second, sulfurous acid, and the formula is H2SO3, and next is sulfuric acid. The formula of sulfuric acid is H2SO4, okay, and in SO3 minus 2, do not exist in a free state, okay. Acids containing two sulfur atoms, acid containing acid containing two sulfur atoms, okay. Acid containing two sulfur atoms. First is thiosulfuric acid. First is thiosulfuric acid. Thiosulfuric acid H2SO3. Thiosulfuric acid containing two sulfur atoms, thiosulfuric acid. And next is second is dithynous acid. Dithynous acid. Dithynous acid. That figure is H2S2O4. H2S2O4. Okay. And next third is pyrosulfurous acid. Pyrosulfurous acid. H2S2O5. And next 4 point, diathynic acid. Diathynic acid. Next is diathynic acid. Okay, diathynic acid, and the formula is H2S2O6. Okay, H2O6. Okay, and 5 point, pyrosulfuric acid. Sulfuric acid. Okay, that is H2S2O7. And R is free acid unknown. Free acid unknown. Free acid unknown. Okay, free acid unknown. Okay, free acid unknown. Okay. Next, peroxy acid. Okay, and next is peroxy acid. Okay, peroxy acids. Okay, peroxy acid. First peroxomonosulfuric acid. Peroxomonosulfuric acid. Okay, carol acids. Okay, that make H2SO3. Second, peroxo disulfuric acid. Peroxo disulfuric acid, that is H2S2O8. That is Marshall acids. That other name is Marshall's acids. Okay, and 3 are more acetum. 3 are more sulfur atoms. That make first is polythionic acids. Polythionic acids, that is H2SnO6, N equal to 2 to 6. Okay, 226 is that dithionic 2 hexathionic acid. Okay, next the sulfuric acid H2SO3 is not known. The sulfuric acid H2SO3 is not known. Okay, but its highly stable salt hyposodium thiosulfate is known. Okay, and the acid which name end with a suffix, all their salts name also ends with suffix. Similarly the acids which ends with ice, their salts name ends with suffix -ate. Okay, H2SO4 is an highly liquid. Okay, H2SO4 is an highly liquid, high boiling point that is 338 degrees Celsius. Selenic and telluric acid are solids. Selenic and telluric acids are solids. Okay, H2SO4 decomposes at rate heat into SO2. Okay, sulfur dioxide, water and oxygen, while H2SiO4 break up into selenium dioxide, water and oxygen at lower temperature 280 degrees Celsius. H2TO4 decomposes at 360 into TeO2, H2O and O2. H2SiO4 and H2TeO4 are more powerful oxidizing agent than sulfuric acid. Thus, sulfuric acid does not oxidize HCl, but H2SiO4 and H2TeO4 liberate chlorine and hydrochloric acid. Okay, H2SiO4 plus 2HCl, that H2SiO3 plus H2O plus Cl2, and H2TeO4 plus 2HCl, that is H2TeO3 plus H2O plus Cl2. Okay, structure of oxy acids and acids of sulfur. Structure of oxy acids of sulfur. Okay, H2SO2, sulfur, hydrogen, oxygen, sulfur, hydrogen, oxygen. Okay, and sulfur is 1 2 1 2 3 4 5 and this, and 1 2 3 4 1 2 3 4 and 5 and 6. Okay, and that is 1 2 3 4 5 6 and 1 2 3 4 5 6. Okay, next hyposulfurous acid. This is a sulfoxylic acid. This is sulfoxylic acid. Okay, and next is hyposulfurous acid. Hyposulfurous acid H2SO4, okay, and the structure sulfur single bond hydrogen, oxygen, okay, and many types of structure you can show. Next is thionic acid. The general formula of thionic acid. Thionic acid. The general formula of thionic acid acids is H2SNO6, that is N equal to 2 to 6. H2O6 is called dithionic acid. H2SNO6 N equal to 3 to 6 is called poly, tri, tetra, penta and hexathionic acids, okay. And the property dithionic acid is quite different from polythionic acids, okay. Next, strength of oxy acids, okay. Strength of oxy acids. The strength of oxy acids depends on the degree of dissociation of the acids. For example, if we take H2SO3 and H2SO4, for comparison we find that H positive ions in H2SO3 is strongly bonded and hence dissociation is less. That is why H2SO3 is a weaker acid than H2SO4. Acidic strength of H2SO3, that is H2SO3 is greater than H2SiO3 is greater than H2TO3, which is acidic strength of acidic strength of H2XO3, okay. As the radius of X in H2XO3 increases, X oxygen bond strength decreases and oxygen hydrogen bond strength increases as dissociation of H2XO3 that make H positive plus HXO3, okay, decreases, and thus acidic strength also decreases. The acidic strength of H2XO4. And the next is second point, acidic. The acid strength of H2SO4 is greater than H2SiO3 is greater than H2TiO3, okay. And acidic strength of H2SO4 is greater than H2SiO3 and H2TiO3, okay. H2SO3, H2SiO3 and H2TiO3. H2SO4, H2SiO4, H2TiO4. Sulfuric acid, stable, strong acid. H2SiO4, selenic acid, less stable, less acidic, and H2TiO4, telluric acid, least stable, least acidic, and acidic strength decreases and acidic strength increases, okay. And a mixture of H2SiO4 and HCl acts like a cure, regia, and dissolves gold and platinum. Selenates are isomorphous with sulfates and form alums, but tellurates resemble with chromates closely. Tellurium also forms tellurates and polytellurates, okay. Tellurium also forms tellurates and polytellurates. And this 16 group is in there, and next group elements of group 17, halogen families, okay.